The next speaker is Professor Jan Vonk. He's going to speak on rational points on modular curve.
All right, thanks very much, and nice to see you all again. We'll continue the story where we left off, but before, maybe I'd like to remind you that there are notes available, which I've been updating on the following URL, which is my webpage. The easiest is probably just via Google, which is what most people seem to have been using. But this is the URL. I think you can omit the pub, and it still works. But anyway, if anyone's unable to find the notes, just ask me after the talk or ask someone else who's been successful at finding them. All right. So last time we talked a little bit about Mordell-Weil groups of abelian varieties. We discussed the weak Mordell-Weil theorem, which was about the group of k rational points on an abelian variety defined over a number field k. And we also discussed the Birchon-Swinnerton-Dyer conjecture. And we gave a sort of explicit form of it for modular abelian variety. Okay. Now, recall that the goal was to use to our advantage, for instance, when we're dealing with elliptic curves over Q, the modular parameterization that was discussed also in other lectures. And so our goal was to produce systematic sets of rational points on modular curves. And recall that we had two main sources of rational points, the first being provided by the cusps, which is really the subject of today's lecture. And the second, which will be discussed later in this course, is the theory of complex multiplication. All right. So today, the story will be about cusps, and in particular, I will give you some tools to compute lots of examples for yourself, which is really the best way to get familiar with them. And I'd like to begin with a computation that probably most of you have already done at some point. If not, here's your chance to do it. And this is all motivated by the title of the section, which is Computing Cusps on Modular Curves. Now, as we saw already today in Professor Gatti's lectures, modular curves are moduli spaces, so they parameterize elliptic curves with some additional structure. And so let's try and write some of them down explicitly. And let's begin very generally with an elliptic curve, E, defined over some field. And let's pick a point P and let's assume that P is not of order 2 or 3. Okay. In fact, we'll want it to be of order 5 in today's example. Now, you see, under just these very general assumptions, we can put E in Tate normal form, called Tate normal. And the Tate normal form, first of all, you see, if you have an elliptic curve and you have a general Weierstrass equation, we can translate by changing the coordinates this point that we picked to the origin. So already we know that the constant term will be 0. And in fact, by elaborating slightly on this, we can always rescale the coordinates to put it in the following form. So y squared plus uxy plus vy equals x cubed plus vx squared, where this is the same parameter v. It doesn't look like a v, so let me try that again. There we go. That's a little bit better. Okay, well now this point P has become the origin. If you do that, in general, you'll have more parameters, but you can use the fact that the point is not of order 2 or 3 to argue that some of the coefficients are non-zero, and then you can just rescale x and y to make sure that this happens. It's a nice exercise if you haven't done it. Okay, so you can put this in this normal form. So everything's very explicit. We have an explicit equation, and it depends still on two parameters. Now what I'm going to do is, I haven't really committed to my elliptic curve yet. It's a general elliptic curve that has such a point. And now I'm going to express that I want this point to have order 5. Yeah? Okay. I'm going to do that algebraically. And I won't write down the equations for the group law because they get already quite large. But I did this for you, and I'm going to tell you what the result is, hopefully encouraging you to try it for yourself. Suppose P has order 5. What happens now? Well, what we can do is we can now express algebraically, using the group law on this elliptic curve, the equality 3p equals minus 2p, which is the same as 5p equals 0, but the equations are a little bit nicer if you do it in this way. If you do that, you find that this equality is equivalent to the statement that u is the same as v plus 1. Yeah. Try it. It's really a nice calculation. Now, if we look back at our original curve here, u, v, v, we found this relation. And in fact, we haven't imposed anything on our elliptic curve other than that there was this point of order 5. So we found really an equation for the universal elliptic curve with a point of order 5. Yeah? Okay, so hence, we have a universal curve with a rational point of order 5, which we might call E sub v. I can eliminate one of the two variables. E sub v is just the family of all these elliptic curves which have that equation where I just replace u by v plus 1. Okay. Now this depends on some parameter v. Yeah, so this lives above, well, projective line with coordinate v. And this is our parameter space for elliptic curves with a point of order 5. So another way of saying that is that we found really that x15, the modular curve as it was defined this morning, is isomorphic to P1. Yeah. In fact, all of this happens over Q, if you like. So this means whichever value I pick of V, and I plug it in here, I'm going to get such a curve with this point of order 5 according to the group law. The only thing I don't know is that it's really an elliptic curve. I have to be careful because some values of V will not be allowed. For some values of V, if I plug them in, I'll get a singular curve. Now, how can we figure out what the forbidden values of V are? Who has any idea how we could possibly achieve that? Let's try some values. What about V is equal to minus 1? Y squared minus y equals x cubed minus x squared. Oh, that's the curve we saw last time, remember? And it's a good thing too, because we already found an elliptic curve with a point of order 5. And here it is in the family. It corresponds to v equals 1. So maybe let me remark that here in brackets. So note, for very specific values, these are just old friends. V is equal to minus 1. It gives the example which we called, I think, E1 last time. And likewise, if you put V is equal to minus 11, that gives this curve E2 from last time. You just want to cross-reference with the notes there. There was also an E3, remember? But that one didn't have a rational point of order 5. So we're not expecting it in this family. Okay. All right, so those are the only two examples that we knew, and luckily we find them as a specialization, but not all specializations will do. There's a discriminant of this elliptic curve that had better be non-zero. And the discriminant, after all, is given by an explicit formula, and I calculated it for you. It's the following. So this curve, this universal curve, EV, has discriminant delta, which I factorized for you to put it in this nice shape, and it is minus v to the fifth. And then I get this polynomial, which is v squared plus 11v minus 1. There we go. Okay. So that means whenever v is a root of this, or infinity, the point at infinity also is not allowed, this is not going to be an elliptic curve. It's going to have a singularity. So in other words, how many forbidden values do we have? Well, the point at infinity, the root 0, and then these two roots of this quadratic polynomial. That's 4 forbidden values. These forbidden values, we call them cusps. Those are the parameters that don't give you an elliptic curve, but a degeneration of an elliptic curve. So we found 4 cusps on this modular curve. We can say a little bit more even, because you see, so we find that 2 of these cusps are special. We find the 2 cusps that come from the values 0 and infinity on this projective line. And they're actually defined over Q. They're rational values of this parameter. This is not true for the roots of this quadratic polynomial. They lie in some extension, they don't lie in Q. Now, what's the extension in which they lie? Who can tell me what they're defined over? They're defined over, who calculated it? Yes, thank you. So Q square root of 5. Okay, keep this one in mind. We'll try and see if we can make sense of this in general, because of course this begs the question, what happens for x1p for some general prime p? How many cusps does it have? And what's the field of rationality of these cusps in general? What is this Q square root of 5 in general supposed to be? Okay. All right, so in the notes, actually, I couldn't help myself and I did a couple more examples. So there's x17 is there, x111 also, which happens to be isomorphic to the curve E1. But these computations get kind of, the equations get very ugly very quickly. So at some point you have to stop, but you can push this quite far, and it's a great exercise to do to familiarize yourself with these in a very concrete and hands-on way. Okay, now, so what happens generally? Let me tell you the recipe. And the reference is, well, there's a little bit more in the notes, and the book of Katz-Maser has a chapter where all of this is explained in great detail. I will just give you the answer and the way to compute them, and then we'll go through some examples and see what we get for the set of cusps. All right, so we'll begin with any congruent subgroup gamma. And so congruent subgroup here means it contains a gamma n, just like in this morning's lecture, where gamma n as before is just all the matrices A, B, C, D in SL2Z that satisfy that they're congruent to one, to the identity matrix, I should say, not it. So this is a general congruent subgroup, and the cusps will be in bijection with a double coset that's very computable in general. So first, it helps to just take the quotient by this gamma of n, using the fact that SL2Z acts transitively on the cusps. And that gives me the following coset space, modulo the stabilizer of infinity, which is plus or minus 110 star. So this is a small group where all my coefficients now are in this ring Z modulo NZ. Okay, so here also this star is in Z modulo NZ. This is a group like so. We're also going to quotient out on the right by this group gamma, or rather by its image in the quotient by gamma of n, which I'll denote by gamma bar. So this is a set. It's a finite set, which hopefully we can compute for any given example of gamma. And it's the set of cusps. Yeah? It's in bijection with the set of cusps. Now, as we saw here, these set of cusps, I mean, they have some field of definition. And that field of definition is also quite easy to figure out. There's an action here of the Galois group of Q on this set. So GQ will be my notation henceforth, or G sub K for any field really. It's absolute Galois group. And it acts on, well, we're dealing with double cosets of matrices here, where the entries are in Z modulo NZ. If I have such a matrix, I'm going to act by Galois on it by acting on the elements in the first column by multiplication by the cyclotomic character. This is for the elements in the first column, where I just act on the cyclotomic field. That scalar that comes out on the root of unity is what I'm going to multiply by. And on the second column, it's going to just act trivially. That's what the action of Galois comes out to. Okay, so this is the general picture. Of course, for any given gamma, it's not so clear how to do that, right? We have this group here, we have the quotient out on both sides by these subgroups, and then hopefully we can say something about the Galois action. The Galois action seems kind of cheap because it's just very explicitly described in terms of the matrix entries. So the main issue is, how do we enumerate all of these double cosets? So here's how you do this in practice. So to compute this double coset, we note that if we start on the left, if we ignore gamma for now, we don't act by gamma yet, we just look at this coset. Yeah, you see, this is interesting because here you can, it's like doing a row reduction. Yeah? You're allowed to subtract multiples of the first row from the second row, so you can always put it in a standard form, in a reduced form. So note that by doing that process, just starting by first ignoring the action of gamma tilde, gamma bar rather, we really get the same as the set of primitive vectors by just remembering the first row after this row reduction. So the primitive row vectors with entries in this ring Z mod NZ, modulo plus or minus 1 coming from this modulo. Primitive here means it's of order n. It's a vector of order n, additively. All right, so for general n, this can get a little bit complicated because you have to worry about the divisors. We were just talking about this over lunch, actually. And the expressions get a little bit complicated. So just for simplicity, let's work out a couple of examples where n is a prime. Yeah? So we will make this explicit now. When n is a prime, so at least I know which group is contained in my congruent subgroup, and now I'm going to take gamma of the following form. Gamma is going to be of the form G intersect SL2, SL2 FP, let me just write. Yeah, everything now, the coefficient field is now just FP, where G is a maximal subgroup of GL2 FP. Now, there's a well-known classification of these maximal subgroups, and they're interesting because somehow, yeah, they come up. For instance, if you study the action of Galois on the torsion of an elliptic curve, the P torsion, then Serre has a theorem that says that this is always maximal image with the, so maximal meaning the full group, with the exception of finitely many primes for every elliptic. So you can try and turn the problem upside down and say, well, now we're going to study the failure of surjectivity by looking at all of those finitely many exceptional primes. And if the image is not the full group, then it's contained in a maximal subgroup. So it gives rise to a rational point on the associated modular curve. And that's really maybe the motivation for picking these particular subgroups. So just to point out, gamma 0 of P is amongst those. Yeah? And that's one certainly that we already have very good reason to care about. And so that's the one we'll start with. Meanwhile, if there's any questions, feel free to interject. Sorry? Yeah, sorry, indeed, absolutely. So gamma bar, really. In fact, can I change my mind and make this a gamma and this a gamma tilde? Because this is the one I'm going to use most often, so it's going to save some chalk. All right. For the first case, there's a classification, and there's 4 types of groups really in this classification. The first one is the so-called Borel subgroups. Which are conjugate to G of the following form with a 0. So upper triangular. So those are the ones that preserve a line. It's a subgroup that preserves a line. This is now a subgroup of GL2 FP. Okay, it's a maximal subgroup. Now, of course, if I intersect now with SL2Z and I lift, that gives me precisely the gamma 0 of P subgroups that we've defined before. Yeah? So the associated modular curve here is X naught of P. Beautiful modular curve defined over Q, and we're going to investigate its set of cusps. Okay, so what are we supposed to do? We're supposed to look at this double coset, one side of which we've already worked out. Yeah? So we're now dealing with row vectors that are primitive, which just means that they're non-zero. Yeah? Everything else will be order P, modulo plus or minus 1, acting on both of the coordinates. And now we're going to calculate the orbits of this group gamma on this set of row vectors. Okay? Now, a number of times, I might forget to put a factor of 2. So pay extra attention. And if I put a wrong factor of 2 or one too many, tell me, coming from the plus or minus. I say that because it's customary to move this plus or minus 1 over to the side of the group to calculate the orbits of plus or minus the group. And then everything changes by a 2. Except the end answer, of course. So if you see me slip in an erroneous factor of 2, let me know. Okay, so what's the relevant formula here? So if I take such a primitive vector, x, y, a row vector, and x and y are elements of FP, and they're not both 0. One of them can be 0, but they can't be both 0. Now I'm going to act by an element of this group gamma, which is the intersection of a Borel with SL2 FP. And a general element here, well, it's upper triangular, so it's got a 0 here, and then here it's got some entry, which I'll call A. It's an SL2, so this entry had better be A inverse, and then here I get some arbitrary element B. Yes? So that's what a general element of my group looks like. Okay, so let's compute what this product comes out to be. Well, that's AX, and then here I get A inverse Y plus BX. Yeah? This is the relevant identity here to compute the orbits. Okay. All right, so we see, for instance, if we had a vector where x was non-zero, then we can reach a lot, because we can multiply it by some arbitrary scalar, and then here we can go completely nuts. And that's, did I do that right? Yeah, I think so. Yeah, okay. So this x, for instance, it was non-zero, and now we can multiply it also by an arbitrary scalar. So we can make the second coordinate whatever we like, and the first coordinate whatever we like, as long as it's non-zero. That's already one of the orbits. When x is equal to 0, yeah, it's even easier actually, because this one just goes away, and we see that here we can just multiply the second entry by some scalar. Y can now not be 0 because x was 0. So Now we just get an orbit which is essentially 0, comma, anything we want. Okay. So to summarize, we have precisely 2 orbits. And in fact, let me put this in a little table. For this particular example, table is maybe not super informative, but nonetheless, let me set it up in this way. So here are my 2 orbits, and I'm going to compute some of the invariants associated. So the first orbit, corresponding to a cusp, is the orbit that we said, where the first coordinate is equal to 0, and the second coordinate is equal to whatever we like. Yeah? That's the first orbit. The second orbit, in fact, maybe I'll call this y, and I'll be more explicit. I'll just say y is in FP. The second orbit is of the form x comma y, where x is in FP star, invertible, non-zero, and y can be whatever it likes. That's my second orbit. A very easy calculation, and so we see that we have 2 cusps here. The size of these orbits also. And now we have to be careful, yeah? So how many elements are in this? Well, P. Right, sorry, this is, oh yeah, so sorry, this should be a star also, yeah? No one saw this, but y also can't be 0. So that's P minus 1 elements, but I have to remember the plus or minus 1. So P minus 1 over 2. But this time I remembered. Sorry? Oh, okay. This one, how many elements are in this one? Well, P minus 1 times P divided by 2. Sanity check, they should add up to the full space of primitive row vectors. How many elements is that? It's P squared minus 1 divided by 2. So that's what it should be. Always do a sanity check with this kind of computation. All right, so we found that there's 2 cusps, and now we want to know what fields they're defined over. Yeah? So now we have to engage with this Galois action that I described here. And it's very easy, right? Because we just have to look at the orbits, we have to look at the coordinates, and we just have to multiply the first coordinate by the cyclotomic character. That's how a general element of Galois acts. And if I do that on the first orbit, I'm just dealing with the element 0. So if I multiply by the cyclotomic character, I'm not doing anything. So Galois acts trivially, in fact, even on all of these elements. It certainly preserves the orbit, and so this cusp is defined over Q. Here it doesn't act trivially on all of the elements because the entries here are non-zero. So the cyclotomic character will act non-trivially, but it'll send elements of the orbit to other elements of the orbit. So it preserves the global orbit. And therefore, this cusp also will be defined over Q. So it's customary to call these cusps 0 and infinity, according to their projective representatives here. And that's usually the name that I will use. In fact, since I set it up on the left, with left multiplication of the stabilizer there, I have to projectivize with respect to the first coordinate. So this one's infinity and this one is 0. That's just a name that I'll give to these. Let me write that down. It's customary to call these infinity and 0. Okay. All right, so we have a very nice picture of our modular curve, x naught of p. In general, it's going to have some curve which has some genus, and we know that inside of it, since y0 of p, so all of the points that actually classify elliptic curves and not degenerations of them, and the complement is the set of cusps, which is just 2 points, infinity and 0. All right, so that was the first maximal subgroup on our list of maximal subgroups that constitute the classification. What about the second one? The second one is the so-called, well, my second one on my list today happens to be the normalizer of a split Cartan subgroup. What does that mean? It means G is the diagonal matrices in GL2FP. That would be the split Cartan subgroup. Its normalizer actually contains it with index 2, and it contains also the anti-diagonal elements. Okay. So that's a group of size p minus 1 squared times 2 in GL2FP. Okay. All right. So this is associated to some modular curve, which we haven't met before, so I'm free to give it a name. So it's associated to modular curve, which is typically called X split with a little plus, where the plus refers to the normalizer of. And if you omit the plus, you usually just mean the split Cartan subgroup. Or you forgot to put the plus, that's also a possibility. But that's the common notation for it in the literature. Okay, whatever it is, it's a very nice modular curve, happens to be defined over Q also. And we can understand its set of cusps with a very similar calculation, except the group is a little bit different this time. So this time, we need the equivalent of that identity. We're again going to act on XY, and we have these two different kinds of elements in our group. Yeah, so I'll just do them both separately. So I'll have an A and then some other element, but I'm intersecting here. I'm in the group gamma, not G. Gamma's intersected with SL2, so this element had better be the inverse of the original A. And that guy, well, that's not so difficult to compute. That's AX and then A inverse Y. Then we also have the other ones, and for them it's enough to actually compute. So we have XY of the element 1 minus 1. Everything else will be products of these two. So if I work this one out, I'll know the full answer. And this one also is not terribly difficult. It's minus Y comma X. Yeah? I might as well put commas to make it more clear. Okay, so these are the relevant identities that we had here. And now we have to determine what the orbits look like. Now you see these orbits here, they have a remarkable property that I didn't really change the product of the two entries. That's a good way of looking at it. And in fact, that's the only thing that's preserved by this. So if I just act by these elements, the product is invariant. If I act by this element, the product is just changed by a sign. And in fact, those are full orbits. So I have a complete description of all of the orbits for this action. So this time, we get an orbit for every possible product of the two entries that we can get up to a sign. And again, the orbit where the product is 0 is going to be a special one. So we get p plus 1 divided by 2 cusps. I didn't say this, but p is always at least 5. I hope I said this at the beginning, but I may have forgotten. Okay, so this time we get p plus 1 over 2 cusps, and in fact, maybe I can put the table here. They look like following orbits. Okay. So I have two types of orbits, depending on whether the product of the elements in this primitive vector is 0 or not. So that's the first orbit. It's just one guy by itself. Is x comma y, and x times y is equal to 0. And I also get x comma y, where x times y is equal to some fixed value I, or it's negative. So for every I get an orbit like this. I don't want to write 1, 2, etc., because I don't know how long this list is going to be. So I call them all like this, and I introduce a new column, keeping track of the amount of such orbits. Yeah? So the first guy is just a unique one. And this guy, I have a choice of my element I, where I is non-zero. Right? I didn't say this, but I is non-zero. So I have a choice of a non-zero element, which gives me p minus 1 choices, and now I divide by 2. So it's p minus 1 over 2 cusps. And if I add them up, I get p plus 1 over 2. That's what I had. So that's looking good. All right, the size of these orbits, also interesting to note. For this one, well, either x or y had to be equal to 0. Yes, so that gives me p p minus 1 choices for the first coordinate being 0, p minus 1 choices for the second coordinate being 0. But then I have to remember about the plus or minus 1. So it's p minus 1. Contrary to what my notes say, which have the factor of 2, but I don't think I want it. Likewise, the same is true here. So the orbits have the same size. All right, sanity check. Multiply this by this and add this, and you get, I hope. Yes, you get p squared minus 1 divided by 2, which is correct. Okay, very good. So now what interests us is the field of definition of these cusps also. So now I have to look back at my Galois action. I know I act by the cyclotomic character on the first coordinate of the vector. So if I look at my description of my orbits here, I see that the first guy really is preserved. Because if it was 0 and I'm acting on it, then it stayed 0, and otherwise I'm just mixing around the elements of this orbit. But this is really preserved by this action, and this cusp is going to be rational over Q. However, if I do the same here, this is not going to be true at all. Because if I act by the cyclotomic character, by some scalar on the first coordinate only and not on the second one, I mess up the product. In fact, I can mess it up however I like. I can mess it up maximally, meaning that I only act trivially when the cyclotomic character is true. So that means, in this case, because we're also quotient out by plus or minus 1, the field of definition is Q zeta P plus. Yeah. So it's the totally, so I can write this more explicitly as Q zeta P plus zeta P inverse. It's the maximal totally real subfield of the cyclotron. Okay. All right, so that's the second type of maximal subgroups. There's a third type. Which is very similar, except it's a normalizer over a non-split Cartan subgroup. So I mean, it comes from a torus embedding as well, but a non-split torus. So not something that we can make up to conjugation equal to the diagonal, but something that's a genuine non-split torus, meaning fp squared star. And so let's get to that one next. There's also the normalizer of a non-split Cartan subgroup. And that's G, which is going to be of the form fp squared. So that's the finite field with p squared elements. And then I take the units in that. And its normalizer again contains it with index 2. And it's inside of GL2 fp. Now this seems a little bit less explicit, right? Before I wrote down coordinate entries, matrix entries for these groups. Here, I'd rather not do that, because already seeing how this group is a subgroup of GL2FP, you don't really want to commit to coordinates. It gets a little bit messy. The way to do it is you take FP squared. It's a degree 2 field extension of FP. And so as a vector space over FP, it's 2-dimensional. So you can pick a basis for it, or not, yeah, but it's a 2-dimensional vector space over FP. And now I can act on itself by the units, multiplication by the units. So I get a linear action on this 2-dimensional vector space, and that gives me an embedding of fp squared star inside of GL2 fp. And in fact, if I change the basis that I chose for fp squared over fp as a 2-dimensional vector space, I just change this embedding up to conjugation. Okay. This normalizer here acts by inversion on the elements here. Very nice action. All right. Now, already here we can feel something coming. We're not going to want to write this out in terms of the basis as we have done before. That'll just become messy. So it's much more convenient. So it's better to view the set of primitive vectors as elements in fp squared that are non-zero. So making this identification of these vectors which live in fp squared or in fp squared these vectors here, they live in fp squared. I'm writing it now because it's difficult just in words to express the difference on the exponent here. Fp squared, and this identification here that I make with fp squared as an fp vector space. So this is where I view a primitive row vector, but I'd rather view it in here under some chosen identification, which also gives me this embedding of this group. So it's more convenient to work coordinate-free, really, in this setup. All right, so to view the set of primitive row vectors, as elements of fp squared star. That's really the set that we're acting on now, and now we're just acting by right multiplication, which is the same as left multiplication, but okay. All right, so now gamma is the intersection of G with SL2 FP. Now you see, if you look in this SL2 FP, the structure of this group, you can figure out, because you see, it's all of the elements of norm 1 in here, because the determinant here gets transferred into the norm. And so that's actually isomorphic to the p plus first roots of unity inside of, that's a mu p plus 1, and then semi-direct with a z mod 2z acting by inversion. That's determinant 1. Okay, so that's what the structure of this gamma looks like. And that's all we need to know, really. We don't need to know much else, because we're acting by multiplication, so we know that's going to be a free action. We're working in a field, yeah, so we can invert that. And so the orbits now, they all look kind of the same. But this time, we get precisely however many orbits this thing has after you multiply out all of these p plus first roots of unity, which are all transitive actions that are simply transitive, in fact, on all of the orbits. Yeah? And so we know exactly how many orbits we get. We get p minus 1 over 2 orbits. Because multiplied by the size of this group, that gives us however many elements there are. Yeah? So we get precisely p minus 1 over 2 orbits, and the table this time, it looks a little bit boring because there's only one entry. All of the orbits kind of look the same, because you see, when you multiply now by an element here, the only thing that you preserve is the norm. If you act by inversion, the norm gets inverted also. So it's very similar to what we saw before. The product being constant is kind of like the norm in the split torus. And I say constant, not really constant, up to plus or minus 1. Here it's the same thing, but a multiplicative constant. Right? So the orbits here look exactly like this. So they're all the elements alpha in fp squared star, whose norm to fp is equal to a given fixed non-zero value of I. So that's what the orbits look like. And they all look the same. So how many elements of I could we have chosen? Well, some non-zero entry. And then we have to also do it up to inversion. So that gives us precisely the number of non-zero elements, which is p minus 1, and then divided by 2. That's the amount of orbits that we see in this picture. Yes, indeed. So everything also there, everything was up to plus or minus 1. So I didn't write that. I think in the notes I did a slightly better job at writing this. But everywhere, in all of these tables, everything is modular plus or minus 1. I kind of did this one implicitly. The same is true here. Luckily, that doesn't affect the norm. Yes. Okay, so we also have the size of the orbits, which this time, well, it's just p plus 1. Yeah? It's going to be normally twice p plus 1, but modulo plus or minus 1 gets me back down to p plus 1. And the field of definition, that's a little bit more annoying. So this one I leave to you because I've described it here in terms of this splitting. So now I need to bring the splitting back to act on the first coordinate. Try this. So to bring the splitting back, typically you choose a non-square in FP and you join its square root. You get some norm form, you get some quadratic form. And on one of the two variables of this quadratic form, you're going to mess with the cyclotomic character. It's going to mess up the value of the norm however you like. Well, by squares, I guess, but that's the same because we're working up to inversion. So that's a nice one to check for yourself to see that the field is really as bad as it can get. It's Q zeta P plus as well. All right, any questions about these kinds of calculations? They're not so bad, right? I mean, they're really quite doable. In the notes, you'll also find gamma 1. And I propose you do that one as an exercise, doing precisely these kinds of calculations. Don't look at the notes yet, and then try it and see if you recover the same result. Yes. No, it's true. No, that's correct. Yeah, but that is also true. Yeah, sorry, I didn't say that. So I always chose a fixed representative, except here, I guess I didn't really. But you'll see that the calculation is really the same. That's where you can prove it. It's a great comment. Okay, so. Sorry, I wasn't done yet, right? Someone was probably already wondering where number 4 was on my list. Number 4, I skip. Just because, well, so there's a 4th element in the classification, which is that of the exceptional subgroups. Which are the G's that, when you quotient them out to, it's a subgroup of GL2, and when I quotient to PGL2 FP, there's all these exceptional subgroups for some values of P. So you can find sometimes an A4, an S4, and an A5 in some exceptional way inside it. And so it's this double cover that you get from these. Now, the arithmetic interest of these subgroups is more limited, and so for that reason, I skip it, omitted, even though there's no particularly good reason to want to skip it. So if you're looking for extra exercises, this could be a good one too. The modular curves associated to them, well, with some notable exceptions, don't have any rational points at all. So this is a known thing, and that's one of the reasons their arithmetic interest seems to be a little bit more limited than the others. They're very interesting curves, but if I have to choose to skip one, I choose that one. All right. Before I tell you about the next theme, which is the theorem of Mann and Drinfeld, I just want to point out one thing. And this is also an exercise for you. So for the group gamma, or yeah, gamma tilde, I guess, being gamma 1 of P, this is an exercise. It's very similar to the computations we just did, and I recommend you do it. We find that there are P minus 1 over 2 cusps that are defined over Q. And there's P minus 1 over 2 cusps that are defined over Q zeta P plus. Does that work with the example we started today's lecture with? Let's find out. So for P is equal to 5, this predicts, or proves really, 2 rational cusps, which we found, and 2 defined over Q zeta 5 plus, which is an alternative description of Q square root of 5, which is what one of you calculated just moments ago. Okay? So it all makes sense, at least. Yeah? And if you want to have some more fun, try and work out x1 of 7 with the state normal form. It's a bit easier if you have a computer already for that one. The equations get a little bit horrible. And see if you see come out that there's 3 cusps that are rational and 3 cusps defined over Q zeta 7 plus, which is a cyclic cubic extension of Q unramified outside set. It's very nice to see that come out of the calculations in practice. I highly recommend you do that. All right, now, what do we do with these cusps? We're in a pretty good situation because I told you we were desperately looking for rational points on modular curves that we could map through to elliptic curves that arise from this modular parametrization, or just their Jacobians, really. And we found lots of rational points here. by just looking at cusps. And the calculations were all very easy. We can get our hands on them in a very explicit way. So wouldn't it be nice if they generate really nice rational points on the Jacobians of modular curves? And that's what we'll address next. So the first thing I have to tell you is the theorem of Manin and Drinfeld. And the theorem of Manin and Drinfeld answers precisely this question. At least it gives some information that we shouldn't hope too much. We shouldn't hope to get too much of the Mordell-Weil group out of these cusps. We can ask, what proportion, and I don't mean that in any kind of precise mathematical sense, of the Mordell-Weil group of J gamma, which is the Jacobian of X gamma, is generated by cusps. The answer is, well, I'm not going to tell you the precise answer, but I'll tell you something, and that's what the theorem of Manin and Drinfeld is telling us, really, is that you only get torsion in this way. In other words, every divisor that gives rise to a point on the Jacobian that is supported at the cusps is necessarily a finite order in the Jacobian. So the theorem of Manin and Drinfeld, well, first of all, it's only for congruent subgroups. So gamma is a subgroup of SL2Z that is congruence. Then any degree 0 divisor that is supported on cusps is torsion on the Jacobian of X gamma. Okay. Now this theorem, it's for all congruent subgroups, but if we can prove it for the principal congruent subgroups, then it follows for any other congruent subgroup which contains it. So it's a further quotient. If it was already torsion above, then by taking a further quotient, it's certainly going to be torsion. So it suffices to prove this for gamma equals gamma n, the principal congruent subgroup level n, some n. Okay. So that's already observation 1. We only have to prove it for these very special ones. Now, how do we get our hands on these? We want to have some sort of expression. How do we express that a divisor is supported at the cusps? How do we think of these divisors? How do we really get our hands on it? It's all about finding the right description of the Jacobian, really. And so here the transcendental description is the most convenient. So we identify the Jacobian of the principal modular curve, which I'll just denote by J of n. So that's the Jacobian of X of n. And I'll look at its C points. And we can think of that as the dual to the holomorphic differentials on it, which are identified with the space of cusp forms. I'll take the C linear dual of the space of weight 2 cusp forms of level gamma of n with values in C. And I quotient out by the first homology group of the curve. So this is the description of the Jacobian, really as Jacobi was thinking about. Okay, now, how do we view a cuspidal divisor as an element of this numerator in this description? Well, it's by integration. So if I have any divisor, really, but specifically a cuspidal one, I can view that as an element of this Jacobian by looking at the integration pairing that I get by taking a modular form F that's holomorphic, so an element of this, and sending it to the integral from S1 to S2 in the upper half plane, and it doesn't matter which lift you take because we're quotienting out by this, of Fz dz. So the modular form viewed as a holomorphic differential on the upper half. Okay, so that's how you identify a divisor with an element of the Jacobian in this description. Okay, and that's what we're going to use in what follows. So we saw, actually just before this lecture started, at the end of Professor Gatti's lecture, he explained to us that, well, we have an identification of Hom, so this dual of S2 gamma of n, viewed as an R vector space. It's a C vector space, but I forget, and I view it as an R vector space of twice the dimension. It's the same as the homology. He described it with the cohomology in S2, but I'm taking a dual here as well, which shifts the cohomology to a homology group of the compact curve. So that's the parabolic one we saw before. Oops, sorry, with R coefficients. So really, we can think of this top factor as H1xn comma R. And saying that some divisor is torsion inside of there is the same as saying that actually viewed as an element of H1xn comma R, it's secretly inside H1 xn comma q. Because if it has q linear coefficients, some finite power of it, it's a finite dimensional vector space, will actually have integral coefficients and so therefore lie inside of there and be trivial in the Jacobian. That's the same as saying it's torsion. All right, so nothing's happened yet, right, in the proof. This is just finding the right viewpoint and the right interpretation of the Jacobian that'll help us in the proof. So how does the proof go? You can find it in the notes, but I still want to tell you about it because it tells us some interesting things. If I have time. Yeah, it's okay. All right. So here's how the proof goes. So the proof goes by first choosing an auxiliary prime, let's call it P, and I want to choose this prime so that it's congruent to 1 modulo n. Yeah? I have many ways of doing that, infinitely many ways of doing that, and it doesn't matter which one you take. So this is a prime. And what I'm going to do now is I'm going to consider the Hecke operator TP, which was defined this morning. And to define the Hecke operator TP, we had to choose coset representative of the principal congruence subgroup, gamma of n. Then we take this matrix P1, and then again the principal congruence subgroup, gamma of n. And I would like to write that as a disjoint union of just left gamma of n cosets. And these cosets are going to be finitely many, going to be k of them, and we'll call them alpha I. In fact, you can make them perfectly explicit, but we don't have to. We'll just choose some coset representatives alpha I. And we'll note the following, and these are really the two key steps in the proof. So think about them and try and unpack them a little bit for yourself and to see how they work. But the idea is very simple, and it's really quite a beautiful one. Now, we're working on the principal congruent subgroup gamma of n. Yeah? If we were to figure out the cusps in the way that I just discussed, it's primitive row vectors without any action, right? Because the gamma bar is just a trivial group in that case. It's just a primitive row vectors modulo n. So if I take any cusp C and I take alpha I of C, they're actually going to be gamma of n equivalent for any alpha I that I take and any cusp that I take. Now, why is that? Well, you see, if this is this row vector with entries in Z mod nz, if I look at this equation that I have here and I reduce everything mod n, then I just get the identity matrix. This one, by definition, the identity matrix as well. This one also, so alpha I has to act modulo n by the identity matrix, which means it just preserves these cusps. Okay, so cusps are not moved by any of the alpha i's on the gamma of n. A second fact, which I won't prove, but that's more of an analytic fact, really, if you will, is that K, the number of cosets here, it's way larger than any eigenvalue of the Hecke operator on the space of cusp forms. In fact, you don't need to know anything about the sharp bounds that we know on these Hecke eigenvalues. A very naive bound will suffice here to show that this Hecke operator, so Tp minus K times the identity, is actually invertible. So K is not an eigenvalue, in other words. This has zero kernel. Now, what this implies, and that's how it goes, is that if I take a cuspidal divisor, Tp minus Ki, and I act on it, you see now I'm using that, I have a cuspidal divisor, and this Tp operator isn't really doing anything. It's just the degree of this Tp operator is all that comes out. But this guy is necessarily an element of H1 x of n comma z. It's a closed loop. I get precisely K actions of alpha I, but they all give me something that's equivalent to the first cusp. So I'm just subtracting the cusp a number of times of itself. So they're all closed loops, and this is an element of the integral homology on the modular curve. Well, if this is an element of the integral homology and this is a rational operator, all I have to do is invert it, and I get that this thing is in H1 with Q coefficients. And that's it. So it's quite a beautiful proof of the theorem of Mann and Drinfeld there. It's all about finding the right description of the Jacobian to work. Okay. Now, is this good news or bad news? It's hard to say, right? If you were looking to produce, I don't know, elliptic curves of very large rank by uniformizing them by a modular curve and then taking the images of lots of cusps, hoping that they were free generators, that's not going to happen. So Mann and Drinfeld tells us that is not the kind of thing you should be expecting from cusps. But on the other hand, being a torsion point does not mean you're a trivial point, right? So you could still have interesting order. In fact, we've seen already some examples secretly in the previous lecture. And I'll tell you a little bit about how that story goes in general. Fortunately, I don't quite have time to do the calculations for you, but you can find more about this in the notes. And since we won't really use it in the sequel very much, I will just refer for the theory of Siegel units to the notes and the references contained therein. And I'll just give you sort of the lowdown of what it's supposed to do for us. Right, so this is still an interesting question. In fact, it's a very interesting question. What is the structure of cuspidal torsion? I look at the subgroup of the Jacobian that's generated by cuspidal divisors. What do I get? Do I always get the trivial group, or do I sometimes get interesting torsion? If we look at the proof of Mann and Drinfeld, it gives us sort of a bound on the cuspidal torsion, because you see, all we had to do here to get from this element, which was in the integral homology, to this element in the rational homology, is invert this operator. So if I express this operator, compute in given examples, I look at this matrix entries of this thing, and I look at all the denominators that I'm getting. The greatest common divisor of all of these denominators is an upper bound for the cuspidal torsion. So at least it gives us a way to sort of compute it and maybe spot some interesting elements, but it's not really an if and only if statement, unfortunately. Luckily, we have a different tool. And so Mann and Drinfeld can be made effective, if you will. Using the so-called Siegel units. And Siegel units, they're fascinating things that are good for a million different applications. But in this particular thing, you should just think of them as very explicit elements. G sub V, they're indexed, again, by these primitive vectors that we've been considering all along. And they're elements with a very explicit Q expansion, which I'll spare you now, but you'll find it in the notes. But they're elements really of the function field of the open modular curve y of n tensor with Q. So that means some finite power of them will actually be a unit on the modular curve. Now, what that finite power is, it's a little bit mysterious. Yeah, so 12n will always do it, but then there's all these different GVs, and some combinations of them happen to actually lie inside of the actual unit group on the modular curve. Now, why is this relevant? Because you see, we have this very explicit construction of Siegel units that gives us these elements in the function field. And if you look at this, this is the units in the function field of the open modular curve. So the divisor of such a beast must be focused entirely at the cusps. In the function field, the only way that it can have poles and zeros, if it has to be invertible, is if these poles and zeros lie at the cusp. Yeah? And so, yeah, so what they do is, I'll just say, this is my cartoon version of Siegel units. They have very explicit divisors, which you can find also in the notes. On X of n, and a divisor is a well-defined notion for an element of distinct tensor Q. And the divisor, as I said, is always cuspidal. And the second thing is we have an explicit description, sort of an if and only if criterion, which is a linear or quadratic algebraic expression for combinations of these guys, so GV raised to some power MV, where I range over all of these primitive vectors V to be members of the actual function field, and therefore to produce relations in the Jacobian in cuspidal divisors. And I won't give you the exact equations, you can find them in the notes. Now, what that does for it is that, look at these words, explicit, explicit, explicit. And it's really very explicit. So just to convince you of that, I computed a bunch of examples for you, and I made a little table which we'll make use of in the following few lectures. So carrying out this procedure, there's two cases really that I want to tell you about. The most classical case is on x naught of p. And this is really already implicit in the work of Andrew Ogg. On x naught of p, there's only two cusps. We already calculated them. They're both rational. And so infinity minus 0 is a torsion point in the Jacobian by Mann and Drinfeld. The only question is, what's its order? In fact, its order has a very elementary formula. So we find that 0 minus infinity has order p minus 1 divided by 12. Well, that's not always an integer. I'm going to take the numerator of this, which I'll denote here by num. Yeah? So it's the numerator. So I write this in lowest common terms, and then I look at the number on top. Okay, very good. For example, when p is equal to 11, our old friend x111, the elliptic curve that we found last time, what does that come out to be? Well, it's the numerator of 11 minus 1, which is 10 divided by 12. That's 5 over 6. Well, that's 5. Isn't that funny? So x111, or x0 of 11, sorry, I should say, we're dealing with x0, which was also an elliptic curve. It has this cuspidal divisor, 0 minus infinity, which has, by this result, order exactly 5 in the Jacobian, but the Jacobian is just the elliptic curve itself. So we already know that x naught of 11 by this business must have a rational point of order 5. And in fact, we found that last time before we knew any of this. Okay. All right, so that's a general kind of theoretical result. For x naught of p, what about x1 of p? That's also kind of an interesting example. No? After all, x1 of 11 also has a rational point of order 5, so we better find that. Unfortunately, the explicit formula for what you get for general P, it's a little bit more complicated. It uses Bernoulli, generalized Bernoulli numbers. So I'll just give you a table, really. Some small values of the torsion. Well, my table will have primes P going along here. And then I will look both at the torsion of J naught P and the torsion of J1P. Now, hang on, you'll say. That's fishy. You just told us how to compute cuspidal torsion. How do we know that all torsion on the Jacobian is cuspidal? Well, we don't really, except we know for these two. So this is in general, there's this funny conjecture, it's called the Ogg conjecture, which says that initially it was stated for this one, that all of the torsion on the Jacobian effect comes from this theorem of Mann and Drinfeld from the cusps. It was proved by Barry Mazur in his work on the Eisenstein ideal. And then for X1 of P now, we also know by a result, I believe, of Ota, that this is actually the full torsion. So I'm allowed to write this, even though I've only computed the cuspidal torsion. All right, so for P is equal to 11, we get cyclic of order 5 and cyclic of order 5. I hope you forgive me for using this notation instead of Z modulo 5Z, just because otherwise it's going to be too messy, this table. So cyclic of order 5, cyclic of order 5. For 13, actually for 13, the Jacobian is trivial of J0. J0 of 13 is trivial. So that one is just a 1. J1 of 13, amazingly, has a C19. It's got a rational point of order 19 generated by the cusps. We know how many cusps. There's 6 rational cusps. And those divisors actually will give you a point of order 19, amazingly. For 17, X0 of 17 is actually an elliptic curve. And you get a cyclic group of order 4 exactly by this formula again, right? So 17 minus 1 divided by 12, well, that's 4 divided by 3, and the numerator of that is 4. So the order is exactly 4, we get a cyclic group of order. For X1 of 17, it's a lot funkier. It's C8 times C73, amazingly. There's a rational point of order 73 on the Jacobian of X1 of 17. Amazing, right? X1 of 17 is a curve of genus 5. It's huge. I mean, you never, how do you get to know some information about the Jacobian? Here, at least we know something about its torsion, and we'll learn much more about its rank very soon. Okay, I'll just complete this table really quickly. So 19 gives me 19 minus 1, which is 18 divided by 12. So that gives me 3 divided by 2. So 3, C3. Here we get C9 times C487. This torsion gets pretty big, as you can see. I have also 23, so I might as well write it, but we're not really going to use it. So here you get a C11 from the formula I gave you, which survives in here, and we get a C11 times a C37,181. Okay, and I'll stop there. So that's as far as I computed the table. Now, it's quite remarkable if you look at this, and there's a bit of history in this whole problem. And in fact, there's a famous paper of Mazur and Tate in which they prove that no elliptic curve has a rational point of order 13. Over Q, this is not possible. And in the beginning of the paper, they say that Andrew Ogg came and gave a seminar talk in Harvard, and both Mazur and Tate were there. And he said during the seminar that he'd found a rational point of order 19 using precisely these kinds of techniques on the Jacobian of X1 of 13. And they write that this just, I mean, I'm paraphrasing here, but they write something like, oh, this blew our minds, and we immediately got to work. And so this entry here is a very famous one, so the C19. What we'll do in the next couple of lectures is discuss this work by starting first with this case. So these two cases here, which are also the two toy examples that we had in the first lecture, which we now explained these rational points of order 15 as being cuspidal torsion points on the Jacobians. And we'll try and do a 5 descent on these to fully determine the set of rational points and prove that the rank is equal to 0. So that's what we'll do next time. And then we'll segue after that into the proof of Mazur and Tate that there's no rational points on X1 of 13, which is a genus 2 curve, by performing a 19 descent on the Jacobian, which sounds terrifying, but actually the argument is very elegant and quite nice. But so we'll warm up and we'll work our way up to it. And then hopefully we'll work our way up to giving you a glimpse of some of the techniques and ideas that would go into the proof of Mazur in full generality of his famous torsion theorem, which we'll get to very soon. Okay, so in the last 15 minutes, in fact, I'd already like to get a start on this 5 descent argument to try and prove that X0 of 11 and X1 of 11, which are both elliptic curves, actually have rank 0. Yes, so in the second row, only the first one is an elliptic curve. So I can put the dimensions if you like. So this is dimension 1. This is dimension 1 plus 4, meaning I've decomposed it into its simple factors. And oh yeah, then I don't know anymore. I think it's maybe 1. Yeah, I don't know. I'm not going to guess because this is recorded. So, but these ones are 1 and 1 plus 4. Here also you get 1 and then genus 0. This is genus 1. This is genus 1, and this is genus 2. Yeah, but the X1s I don't remember. That's a good question, actually. I don't know the work so well, so I'm a bit iffy on that, but my impression was that he proved Ogg's conjecture, showing that really all the cuspidal torsion accounts for all of the torsion on the Jacobian. Yeah. Whether that comes with an explicit description of the group structure, I don't know. I wouldn't dare to say, but I can look it up and we can discuss it. Yeah. I'm not sure. I don't know this area too well, but I think, so at least we have formulae. So the formula for X1, I think, is already in Kubert-Lang's book, if I'm not mistaken. I think for non-split Cartan curves, there was a student of René Schoof, who graduated in 2016, I think, around that time, who worked out also a formula for the size of the cuspidal torsion, which is interesting because the torsion is not defined over Q anymore, right? I just showed you all the torsion is over the cyclotomic field. So he's working over the cyclotomic field. And he gives a formula for the size at least. Maybe he also gives a description of the group structure. I'm not 100% sure. For X naught of P, of course, we know. And for split, I'm sure we also know. But yeah, but I don't know the exact reference. I can look them up. In fact, I'll try and put them in the notes in the next update. Okay, so this was sort of the message that we had, is that Mann and Drinfeld may seem like a disappointment at first sight, but in fact, Maser made very profitable use of the size of this torsion that is produced by cusps. Maser makes use of this torsion in a descent argument. And I'll put an exclamation mark because that is quite a striking thing if you're working with these big primes. So we're going to explore it, starting with, well, we start with x1 of 11, which is an elliptic curve, and it has a forgetful map to x0 of 11, which sends the point that rigidifies the elliptic curve to the subgroup generated by it. Now, this is a degree 5 map, and the 5 is 10 divided by 2 because of plus and minus. The kernel of that, we already found out last time, is actually generated by a rational point. Yeah, so there's a z mod 5z inside of it. I better write 0 here. And there's this isogeny. Okay, now all of this works over Q. The first idea of Maser is to spread this out over Z. In fact, for this particular argument, it's enough to spread it out over a slightly less scary ring, namely Z1 over 11. Because 11, of course, is the unique prime of bad reduction. And if we stay away from it, we have actually abelian varieties, which, actually smooth curves, I guess I should say. Well, they are abelian varieties because they're genus 1. And I'll denote these by these kind of script letters. So this is automatic. This isogeny just spreads out to an isogeny over Z1 over 11. They're abelian varieties. The only question is, what is the structure of the kernel? No? Is it still finite flat group scheme Z modulo 5Z, or is it something else? That's the first question that Maser has to answer. In fact, here it's not so difficult to see that it's Z mod 5Z all the way, also integrally, by just looking at the torsion point that we have in hand. It has an explicit coordinates in terms of the Weierstrass equation. And what we're asserting here is that when you reduce it modulo any prime other than 11, it's injective. So the torsion injects. And by the way, if you read Silverman, you know that this is automatic at all of the primes other than 5. So maybe at 5 you have difficulty, but at 5 also it's fine. You can check this explicitly using equations. And if you want to justify this kind of step, which we'll have to do next time when we use this kind of argument on x1 of 13, we use the classification of finite flat group schemes of Oort and Tate, which is a bit more technical, but for now we can do everything with explicit equations. Okay, so we have this exact sequence of schemes over Z1 over 11. Yeah? What we're going to do now is we're going to pass to the associated Selmer exact sequence by taking just the invariants. Yeah? So the Z1 over 11 points of these two guys is the same as the Q points of their generic formulas. Yeah? They're abelian varieties. And so we obtain from the general descent formalism it gives an injection of x0 of 11 q modulo the image of this isogeny phi of x1 of 11 q into, and what I'll do now is you can use Étale cohomology just like in Silverman, but I'll rephrase it already more geometrically by just saying that this now injects, by viewing all of these schemes over Z1 over 11 as Étale sheaves, into the first Étale cohomology group of spec Z1 over 11 with coefficients in Z mod 5Z. If you don't like this highbrow language, it's exactly the same as the Galois cohomology of Q with values in Z mod 5Z that is unramified outside of 11. It's just a change of language. Now that Galois cohomology, it's very computable. In fact, I can tell you this is isomorphic to F5. Meaning it's a cyclic group of order 5 additive group. Why is that? That's because, what does this classify? If you look at the kernel of that map from the absolute Galois group of Q into Z mod 5Z, that's the fixed, that's the absolute Galois group of the fixed field. And the fixed field is a cyclic extension, cyclic of order 5, that is unramified outside of 11. And of course, there's only one such extension. There's a unique extension. I should say, there's a unique Z mod 5Z extension of Q that is unramified outside, well, infinity I never see with this geometric language, and then also 11. I mean, and rather than being so mysterious about it, I'll tell you what it is. I mean, it's Q zeta 11 plus. So using class field theory, you quickly come to this conclusion. The Kronecker-Weber theorem tells you that any such extension must be cyclotomic, contained in Q zeta 11, and therefore you get this. So that's great, because this group is now a subgroup of a cyclic group of order 5. So that gives us an upper bound already for this quotient. But we already know that the size of this is at least 5. Why is that? Well, because x0 of 11 has a rational point also. We've quotiented out by this one. We're not reaching that one in the Mordell-Weil group. So that quotient at least contains 5 elements, and at most 5 elements, so it's exactly 5 elements. So that's the nice thing about this kind of descent arguments. It's the first step where you get the upper bound. And if the upper bound and the lower bound coincide, you're done. You're good to go. So all we need to do is consider the dual isogeny also. And then we'd be done with the 5 descent. But that doesn't seem so difficult so far. Unfortunately, if you do the dual isogeny, the kernel is a mu5. It's not generated by a rational point. The point is only rational over the cyclotomic field adjoint zeta 5. So this kind of argument looks a little bit different because we would be computing the Étale cohomology of mu5 over spec Z1 over 11. And we'd love to use the Kumar exact sequence to solve that. Just like in Silverman, whenever you do a descent, you always use Kumar theory. So we'd love to continue to use Kumar theory, except in the Étale topology, the Kumar sequence is not right exactly. And that's because 5 is not invertible in Z1 over 11. We haven't inverted 5, you see. So either we do that and we end up with a bigger Selmer group that is going to be hopelessly too big, or we have to refine it. And so that's what we'll do next time. So for the dual isogeny, and this isogeny, goes this way. We need to refine the argument. I'll explain next time how to do that. And the way that this is done uses quite technical tools. So we'll use, instead of the Étale cohomology, which is already technical enough, we'll use the finer flat topology. So we'll use the flat cohomology. Now, if you've read Milne's book on Étale cohomology, this will not be a scary thing to you at all. But if you haven't, it's actually okay to just follow along the argument, and you'll be able to appreciate lots of the nice ideas if you're willing to take a couple of things on as a black box. And so I'll just tell you what those things are, and then we'll stop. So we're going to work in the finer flat topology. And for those of you who know what that means, that's the topology that's generated by covers which, if you specialize to affine subsets, the covers must be of the form well, the family must be jointly surjective, topologically. And the phi i's must be flat and finitely presented. Okay, so that's just a bit of technical. That's what this topology looks like for those of you who've seen this kind of thing before. Now, what are the advantages? And this is really the two things that's all you need to know, really. And if you take those as a black box, you can really appreciate the argument without hopefully being too put off by this language. Whenever you have a sequence of schemes like this one or this one, it's an exact sequence in the Étale, sorry, whenever you have a sequence like this of schemes, it defines for you an exact sequence of sheaves in the Étale topology. That's what I've implicitly used in this kind of descent argument. And the same continues to be true of this finer flat topology. So it's finer, but it's not too fine, so that schemes are still FPPF sheaves. Yeah, that's usually the adjective that's put instead of flat. So it's the FPPF side. They're still FPPF sheaves. And crucially, the Kumar exact sequence, and that's the only thing we'll use really, these two facts. Is exact in the FPPF topology. And using just those two facts, and so the Kumar exact sequence, I'll remind you, it's the sequence that defines mu n by taking gm to itself, by taking the n powers. That's actually right exact. And we saw this already in the first lecture when we proved the weak Mordell-Weil theorem. We had to somehow pass to an extension to make sure we had to invert, rather, all the primes that divided n in our base, which led to a worse Selmer group. It was bigger. The estimate, the upper bound that we got was bigger because of it, but it came with the advantage that we could use that the Kumar sequence was exact. Now we don't have to do that. So we don't have to invert the primes that divide n, or the primes that divide 5 in this example, at the cost of working with this slightly fancier topology. And we'll see that if you just take those two facts on faith, you can happily apply the formalism and appreciate the nice ideas in the arguments of Maser, doing this 5 descent on x1 and x0 of 11 in first instance before we move on to the 19 descent on the Jacobian of x113 using very similar arguments. From that, we'll be able to appreciate also how the general arguments go, at least to some extent. So with that said, I think I'll stop there and I'll see you tomorrow.
Any questions? There's a question here.
Yeah.
That's the spread out exact. Okay, so we write the exact sequence for the dual isogeny over Q, and then we want to spread it out over Z,
Yeah.
1 over 11. Is this one not exact 2 in the étale topology?
It is, but we don't know what the kernel is a priori. So we know that it's going to be a surjection. It's an isogeny of abelian varieties, but we don't know what the structure of the kernel is. It's some finite flat group scheme, so we know that because it's the kernel of an isogeny of abelian varieties, but we don't necessarily know which one. We know, however, that in the generic fiber, it's isomorphic to Z modulo 5Z. And in fact, the classification theorem of Oort and Tate tells you that's enough. And it's enough because you're working over a base field where the ramification index, which is just 1 in this case, is strictly less than p minus 1. And that's enough to conclude from the classification that they're the same. In this case, you don't really need this fancy theorem. You can just look at the coordinates. You take the point and you show that it's actually ejective modulo all of the primes, including 5. And once you've shown that, you know that that has to agree. This is a risky closure. It has to agree with the kernel of this isogeny, and then you're done. So you could spread out in 2 different ways, one being very concrete, one being very fancy. Unfortunately, in general, the fancy one is the only one that remains somehow.
I was asking, in fact, about the dual isogeny.
Ah, yes, mu5, similar argument.
Okay.
Yeah, so from mu5 also, you know, it's a finite flat group scheme, and you know that it agrees with mu5 in the generic fiber. And that's actually enough, again, because the ramification index is small. So as long as you're not over a very ramified base, which in this case we're just over Z, you know, so it's not ramified at all, then you can apply Oort's Tate. Characteristic 2, you'll have more issues, but that's a different story. Luckily, we don't have to engage with it.
Thank you.
Any more questions?
Ah, yes. Yes. Very big, yes. So like I said, there's a formula for it. So for the full size, but I wouldn't know how to extract from that formula which big primes come out. But that's just my ignorance. That's not because nobody else knows. It's just because I don't know, which is usually the case, I would know. But it might well be possible that you can say exactly where this 73 comes from. But all I can say really is that it comes out of the computation. Either you compute them on these concrete examples like I did, or you use the general formula, and it's some product of generalized Bernoulli numbers, and magically some integer comes out, and that integer happens to be divisible by certain primes. Whether you can say beforehand what those primes are, it's maybe a bit more mysterious, but maybe I'm saying something very silly now. Let's think about it later today.
Any more questions?
Yeah. It's an excellent question. I completely swept this under the rug, of course. I just told you what it is, and then you just had to believe me. What it comes from is the moduli description of the cusps, really. So the generalized, so you start with a Néron n-gon, which is just Zn copies of Gm, and then you know what the torsion is exactly on that. So the n torsion of that, it's generated by an nth root of Q and an nth root of unity, the zeta n. And you know exactly how Galois acts on there. And so what these row vectors are remembering is precisely which coordinates you have in both of them. So Galois acts by the cyclotomic character, because if it's a zeta n, on the first coordinate, and trivially on the second. So that's where it comes from. It's a very justified question, because I completely didn't tell you. Yes, in Katz-Maser, this is definitely all explained, chapter 10 or something, I think. Maybe also Diamond Ibn has this at some point, but it's very terse, so it's a little bit tricky to extract from the literature. But it's all in Katz-Maser.
Any more questions? If there is none, let's take this speaker again.